Hello, in this video we're going to talk about the latter part of Chapter 2, where we talk about the atomic structure of the atom, isotopes, and ions. Your book has a very good description of the historical events that led to the discovery of the nucleus, and I encourage you to take a read through that. From the discovery of electrons, to the discovery of radioactivity, to the discovery of the compact nucleus, and the neutron. And all of this led us to our current model of the nuclear model of the atom, where inside the nucleus you have the proton and the neutron, and then outside, the rest of the atom's volume is the domain of the electrons. The nucleus is a very dense central core of the atom. The amount of mass packed into such a small amount of space is very impressive. It consists of the protons, which have a positive charge, and neutrons, which have a neutral charge, or no charge. The mass of the proton and the neutrons are both slightly different than 1, due to the fact that as you put together or pull apart different nuclei, you add or lose mass, because energy is absorbed or released in this process, and that energy is equivalent to a tiny amount of mass. For the lighter elements, there tends to be a roughly equivalent number of protons and neutrons in the nucleus. But as the element gets larger and larger, the nucleus gets larger and larger, there tend to be more neutrons than there are protons out here. This is sometimes called the band of stability, depicting roughly how many protons and neutrons are in each nucleus that is stable. Electrons reside in the rest of the volume of the atom. The mass of an electron is much smaller than that of a proton. Electrons are negatively charged. I should have said this on the last slide. This charge is in units of coulombs, which is the SI standard unit of charge. And here it's negative. You'll notice that the charge on this slide is the exact same number as the charge on a proton with a different sign, because the electrical charges have to balance exactly. Okay, so electrons are much smaller. The stereotypical picture of an atom is something that looks like this. We sometimes call this the planetary model of the atom because it looks like the electrons are orbiting the nucleus. That's not actually true. A more correct model is to talk about orbitals, and so you have these various shapes that we draw either as a sphere for s orbitals or various other shapes that are probability distributions. Your likelihood of finding the electron has some probability in these areas, and then we enclose the area of 95% probability into a solid-looking shape. We talk about this a lot in Chapter 5, and we'll get back to it then. So most of the volume inside an atom is empty space. The electrons are really small. The nucleus is still fairly small compared to the size of the atom. If you have the Colosseum in Oakland and you drop a marble on the 50-yard line, the marble represents the nucleus, and the whole volume of the Colosseum represents the overall size of the atom, where the electrons are. It's really quite impressive when you stop and think about it. We define the atomic number as the number of protons in an atom. This number of protons defines the element. 6 protons is carbon, 1 proton is hydrogen, so on and so forth. In chemical reactions, the atomic numbers of all atoms stay the same, i.e. the atoms are unchanged, just their connectivities or charges may change. The big exception here is nuclear chemistry, but we're not going to get into that at the moment. Now the mass number is the total number of neutrons plus protons, and we have a formalism where we write the element, symbolized by X in this case, and the mass number goes on the top left over here, the atomic number goes on the bottom left over here, and that's how we describe the element. However, since the atomic number and the symbol are redundant, you can often just omit the atomic number on the bottom and have your mass number on top, and this would describe exactly what you need to know. So if you're doing some problem in Gen Chem and you're asked to give the symbol for this element in AZX format, that's this. And if you're asked just give the symbol the element, then this is fine over here. So some practice. Write the symbol in AZX format for carbon with 7 neutrons, fluorine with 10, and manganese with 30. Consult your periodic table, pause the video, give it a try, and then we'll put the answers up. Okay, so how do you approach these problems? Well, first you need to find out how many protons are in a carbon atom. And if you look at the periodic table, each individual box will have the symbol really big here in the middle. For carbon it's a C. And then somewhere up in the top there will be a number that denotes the number of protons. And for carbon that's 6. And so you look at this and say, okay, carbon has 6 protons. And you know that the symbol is a C. 6 protons is the atomic number, and so then that goes down here on the bottom left. And then the mass number is symbolized by A, and that's equal to 6 protons plus 7 neutrons equals 13. So then you write the 13 up here, and then there's your answer. When you do fluorine with 10 neutrons, you'll see on the periodic table fluorine has a symbol of F, fluorine has 9 protons, and if it has 10 neutrons, that means that, well, 9 plus 10 equals 19, so you'll have a 19 like this up here. When you have manganese, the symbol here is Mn. Be careful not to get manganese confused with magnesium, which is Mg. So manganese has 25 protons, so the 25 goes down here. Then the number of neutrons plus the number of protons makes 55, and that goes up there. Okay, so this is how we denote elements with a specific number of protons and neutrons in this format. Now, 2 atoms of the same element will have the same number of protons, but they can have different numbers of neutrons and still be the same element. And those atoms are called isotopes of each other. So the definition here is atoms with the same atomic numbers, but different mass numbers, so the number of neutrons vary. Some examples here: uranium-235 is the fissile isotope of uranium, so that's the one that can form a nuclear explosion or nuclear power, whereas uranium-238 is non-fissile and it will not start a chain reaction that's useful for these purposes. Other common examples is hydrogen has 1 proton, 1 electron. This little ring out here is symbolizing that there's an electron here. Not a great way to draw it, but it works. And then hydrogen 2 is often called deuterium, and that has a proton and a neutron in its nucleus. And then hydrogen 3 is called tritium. And there's many other examples. These are just the ones I have here. Here's a table from your book describing naturally occurring isotopes of some common elements. So now we get back to the question of why carbon in the periodic table is not 12, but instead is 12.01. So remember, all of the atomic mass units are defined relative to carbon 12, but carbon 12 does not make up all of the naturally occurring carbon in our planet. You have 98.9% of all carbon is carbon 12, but then 1% of this is carbon 13. So we say that the natural abundance of carbon 13 is 1.1%. For every 100 carbon atoms, say, that you pull out of the ground, one of them is a carbon 13 atom. And so we need to average these all together when we do calculations with the periodic table, because we're dealing with many, many more atoms than 100 anytime you do chemistry. And so we need to get an average. To calculate average atomic mass, you do a calculation something like this. You'll take the mass of carbon 12 and its natural abundance, and then you convert this into a decimal form. Remember, this was 98.9%. So you convert that into a decimal form, and then you have the mass of carbon 13, and then its percentage is a decimal form. And then when you do the math here, you get 12.0107 atomic mass units, and that gives you the number that's listed in the periodic table. So here's an example for you to do. What's the average atomic mass of chlorine? Chlorine consists of 2 isotopes. Here's their natural abundances. Here's the mass of each isotope. Pause the video, try it, and then I'll put the solution up in a minute. Okay, so you take the average mass of the chlorine-35 isotope and multiply it by its natural abundance as a percentage on the left. Then you take the mass and the natural abundance of chlorine-37 on the right, perform the math. So each intermediate result on the left and the right has 4 sig figs, but that translates into 2 decimal places for the number on the left, but 3 decimal places on the number on the right. So that means our answer is going to be truncated to 2 decimal places. In this case, it's still the same number of sig figs that we started with, 4 sig figs. And our overall answer is 35.45 for the average atomic mass of chlorine. If you knew the natural abundances better, you could get a number with more sig figs and more precision, but that's the numbers you were given here. Okay, now we need to talk about ions. An ion is an atom or molecule that has a net positive or negative charge, and these are exceedingly important in chemistry and biology. So, for it to have a net positive or negative charge across the atom or molecule, you need to have a different number of protons and electrons. Those are the things that have negative and positive charge. So a cation is something that has a net positive charge, and you can remember this by thinking that cats are positive. This is Mr. Finnegan, that's my kitty's name. And a cation will have more protons than electrons to give it this net positive charge. Whereas an anion has a net negative charge. Those of you who don't like ants, you can think of this that ants are negative, and then that means an anion is negative. Therefore, an anion has more electrons than protons. You'll hear this term come up in chemistry, a polyatomic ion. It contains more than one atom, but overall it's an ion. So when we write the notation of ions, you put the charge of the ion as a superscript to the right of the number. So for sodium, when it's lost 1 electron, it has a little plus up there. If something's lost 2 electrons and has an overall net charge of positive 2, then you'll write 2 plus over here. Most people write it 2 plus just because. You can write plus 2 and that's okay, but just be aware that I usually see 2 plus instead of plus 2. Alright, similarly chlorine is a negative 1 ion, sulfur can form a negative 2 ion, it would look like that. Now how do we talk about these things? Okay, cations, when you're naming them, it's pretty simple. You just take the element name, you put a space in there, and you say ion. So this is the sodium ion. That's pretty straightforward. When you're doing an anion, you have to change the suffix. So for chlorine, you take the element root name, which in this case is chlor, and then you put an IDE suffix on it. So chlorine becomes chloride. We do this suffix convention a lot in chemistry, so keep track of it. And that's how you name an anion. You'd say this is the chloride anion. So some practice. How many protons and electrons does the sulfide anion have? Okay, so you look this up on the periodic table over here, and you'll see that the sulfur has 16 protons, because it sits right here with the number 16. And now if it's a negative 2 anion, that means it has to have 2 extra electrons, 18. I want to introduce some vocabulary here. Isoelectronic means something with the same number of electrons. So lithium plus 1 and beryllium 2 plus are both isoelectronic because while they have different number of protons, they have the same number of electrons, and that makes them isoelectronic. So here's our question from 2 slides ago. How many protons and electrons does the sulfide anion have? So now we can think which of these new options are isoelectronic with the sulfide. So think about this, pause the video, and then replay it, and we'll talk about the answer. Okay, so the chloride anion has 17 protons because it's chlorine, and then since it's a negative 1, it has 18 electrons. And well, since the 18 electrons is the same as our sulfide anion, we can say yes, this is isoelectronic. Let me drop the drawing and put this check mark up. Okay, if you were to have Cl2-, well then it has the same number of protons but now an extra electron, and this is not isoelectronic. Argon has 18 protons and 18 electrons as a neutral atom, and so that would be isoelectronic. The sulfur 1- ion has only 17 electrons, that's not isoelectronic. And the oxygen anion has 10 electrons, and thus it's not isoelectronic. So electrostatic is a physical force that's very similar to static electricity that you've experienced throughout your life. It's that same force that will hold positive and negatively charged things together. In this case, the atoms will exist in a repeating three-dimensional lattice of different forms. There's many different types of crystal lattices, but it's always a neutral overall combination. You have the same number of positive charges as you do negative charges. So you'll have a cation and an anion. The cation is usually a metal, but it could be ammonium, which is a cation, or some other nitrogen-containing molecule. An anion can be either a nonmetal like chloride or some non-metal compound that's a polyatomic ion. And so we typically call anything that's an ionic compound a salt. In your everyday usage, you use salt to refer to table salt, sodium chloride, but you could refer to lithium fluoride as a salt. You could refer to this protein as the sodium salt form. Anything that's an ionic compound you can talk about as a salt. So something to note is that since there's no discrete molecular units, it's a little weird to think of the molecular mass or the molecular weight. So instead we call it formula mass. And you just take the lowest number integer ratio and figure out what the mass of that is. So the formula mass for calcium fluoride, you take the mass of calcium, 2 times the mass of fluorine, and there you go. That's the formula mass for calcium fluoride. And you just treat it like it's a CaF2 unit. And that's all we have for the moment, so thanks for your attention and patience.